So power functions and radical functions. Going to go on page 31. Just 31. Again, graphing and analyzing the functions and solving radical functions. All right? That's why you guys have the graphs there. You guys will be gluing them in because a lot of this, it really needs to be seen through examples. Okay? So we are going to be graphing a lot today. So that's why you guys have the graphs there. You'll glue them into your notes. Everything else, though, is going to be handwritten. Okay? Everything else is going to be handwritten. So, start out. Okay? What is a power function? Well, a power function is in the form of f of x equals ax to the n, where n is a non-zero constant number. And you can have 4 different situations that can happen when you have a power function.
Wait, we're supposed to write down a graph, right?
Yes. So get these graphs down into your notes, okay? And again, you have these 4 different situations that you can have. A represents the coefficient. It's the number that's in front of your variable. N represents your exponent. Another word for that would be your degree, okay? So n is an even number. So if your exponent is an even number, 2, 4, 6, 8, and a is positive number, then basically you have a graph that's going to look similar to the one that's over here on the left, top left. Basically, both of your n's are going to be pointing up. However, if n is even and a is negative, it's going to be opposite. It's going to be pointing down. Okay, the best correlation that we can have to this is the functions we just did in quadratics. Okay, right? Quadratics, the exponent was what number? It was a 2, so it was even. And whenever we would have like x squared plus 2x plus 3, didn't it point up? Okay, that's because it was an x squared. It was a positive number. But if it was a negative, it pointed down. Now, if n is odd, then basically you're going to be having your n's pointing different directions. One's going to go up, one's going to go down. But if a is positive, it's going to go up to the right and down to the left. And if a is negative, it's going to go up to the left, down to the right. Okay. So now let's look at some examples, okay? You're going to graph and analyze this function, 1/2 x to the 4th. Okay? Yeah, now this is actually going to go into the grid. Your grid looks just like mine. And we're going to find these 7 things. We're going to find the domain. We're going to find the range. We're going to find the intercepts. We're going to find the end behavior, which I'll talk about a little bit more. The continuity, and where the function is increasing and decreasing if there's any. Okay? So I would suggest, maybe we can do the information we're going to make a table. Okay, to graph these, we're going to do tables. So you're going to need space for a table, and you're going to need to fill in all this information. So your choice on how you decide to set this up. We are going to make an XY chart. So we're going to make a table to graph this, okay? Nice little XY table. I mean, hey, that's the best way, honestly, to graph any function, especially if you don't know what it looks like, okay? What number can we pick? What number would be a good idea to pick? -2? Yes. -2, -1, 0, 1, and 2. We pick those x values and we plug it in to find our y values, okay? Order of operations says we do what first? The exponent. So what's -2 to the 4th power? No? 16. So this is going to be 16 times 1/2. What's half of 16? 8. And yes, there's a positive 8 because when you raise a negative number to an even power, it's always positive. Let's do -1. What's -1 to the 4th power? 1. And then what's 1 times 1/2? That. What about 0? What's 0 raised to the 4th power?
0.
Times 1/2?
0.
Awesome. We plug in 1.
Same thing.
It's going to be 1/2. When we plug in 2, it's going to be 8. Yes. And all honesty, guys, before we even made the table, we could have looked at this and said, hey, my degree, my power, is it even or odd? Even, which means it's going to look like this one on the left or this one on the right. But A is it positive or negative? Positive, so it's going to kind of look like this. Okay, so we kind of had we should have had an idea of what it should have already looked like, kind of like a parabola, so things are going to repeat. So So let's graph this. We have negative 2, 8. I know 8's not on there if you count by ones. If you want to change the scale, by all means do you, boo-boo. Okay? But you know, just know that's making a U. Okay? I'm not really going to change my scale. I just know that 8 is somewhere up here. Negative 1 and 1/2. I'm in between 0 and 1. 0, 0. 1 and 1/2. 2 and 8. So this is basically making a nice old parabola type. Okay? Alright, so let's analyze what do you think's happening with the domain? Right. All real numbers. Let's write that in interval notation. That is awesome. Now the range relates to which variable? Your y's.
0 to positive.
0 to positive infinity. It goes no lower. Goes no lower than 0. Is 0 included?
Yes.
So we have a bracket. Awesome. Intercepts. These are your x and or y intercepts. Where does this graph cross the x or y intercept? 0, 0. Okay, so in that case, both the x and y intercepts are both 0, 0. And yes, you write these as points. We'll come back to end behavior. Continuity. That goes back to the very first lesson in this new unit. Is this a continuous function? Yes. So continuity is all real numbers, okay? It's continuous on the whole thing, okay? Yes?
If it's a continuity, would it go by its domain? Like, whatever the domain is?
Exactly. Yes.
But I thought
That will, well, I'll take that back. It's a mix of both domain and range, okay? Remember, if it's discontinuous, it's going to have one of the three. What are the three?
whole,
Infinite, jump, okay? Increasing. Is this function increasing anywhere? This goes back to unit 1.
Yes.
0
0 to
to infinity.
infinity. Is it decreasing anywhere?
No.
Negative to 0. Remember, when you're trying to determine intervals of increasing and decreasing, you always read from left to right. So if I wanted to trace over this graph, I am decreasing from negative infinity all the way to 0, and then I'm increasing after that. Okay? And we always base off of our x values. Okay? Now, in behavior. In behavior is basically asking what's happening as x gets really, really big. What's happening to the y's as x gets really, really big? And vice versa. What's happening to the y's when x is getting really, really small, like getting closer to negative infinity, closer to positive infinity? What's happening? What's happening at the ends? Exactly. As x gets bigger, like of course after 2, it's going to continuously get bigger and bigger and wider, correct? So as x gets bigger, what's happening to your y's? It gets bigger. Now you're gonna say that with a number. So as x approaches infinity, y is approaching infinity. It's getting bigger and bigger. As x approaches negative infinity, what's happening to your y's? It's still going up, isn't it? So it's going to be approaching positive infinity. And the way you write in behavior, okay? Back in algebra 2, you used to do the whole arrow and diagram, okay? This is pre-calculus for a reason, okay? In behavior, it's written as, I'm going to write it up here because I can't squeeze it in here. I want to make sure everyone can see this. It's written as the limit as x approaches infinity of f of x. You've seen this notation before, haven't you? Yes. So now instead of being a number, it's infinity. We're trying to figure out x is bigger, y is approaching infinity. Okay? That represents the right side. As x approaches positive infinity, y is approaching positive infinity. And you guys can write this literally like side by side. You can put a comma, write it side by side on your notebook line. Or if you want to go to the next line, you can. But we need to do both sides, because there's two sides to this problem. There's two end behaviors. You got the right end, you got the left end. As x approaches negative infinity, what's happening to your y's? It's approaching approaching infinity. And to be honest, guys, if A is positive and N is even, it's always going to have that type of behavior. It's always going to point up, and it's always going to be approaching infinity. Okay? And there we go. We just analyzed this power function. All right? Yes?
So based on the A, it will determine the behavior, and what's it like? The A determines basically everything.
It's A and N together.
So
Because N will tell you both will go up, or one goes up, one goes down. And then the degree tells you, the coefficient in front tells you both up, both down. So they both matter. We're going to graph and analyze negative x to the fifth. Lots of graphing today. When you use those same values, when you plug in a -2, do your order of operations, okay? This is a -2 to the fifth power. When you raise a negative number to an odd power, the final answer is going to be negative. What is 2 to the fifth power? So it'll be 32. So this will be a -32. But because you have a negative on the outside, it's going to turn into a positive 32. When you plug in a -1, -1 to the fifth power is going to be a -1. But because you have a negative on the outside, it's going to be a positive. 0 is going to be 0. It's going to be a -1 and then a -32. So when you plot these, yes, this one's going to be like all the way up here somewhere. But then I'll have to be a -1, 1, 0, 0, 1, -1, all the way down.
that looks so simple.
And realize, guys, it was negative and it was odd. If it's odd, it should be going opposite directions. And because it's negative, it should be shooting up to the left and down to the right. Okay? So it should look just like this one. That's why if you know these, you can kind of have an idea when you graph it, like, okay, this graph looks nothing like it's supposed to look. What's going on? Okay? I'll give you 1 minute to to analyze it. I'll give you 1 minute to analyze. All right.
Decreasing from 0 to -50.
You said it's decreasing the whole time, right? So it's decreasing.
From infinity to negative. No, negative.
Monica, give me something, anything. Your choice. It is continuous, yes. It's continuous on the whole thing. No types of discontinuity, good stuff. Christian, give me something else. Doesn't matter, give me anything. Then I gotta go over. Is. Very good. Malaysia, give me something else. I missed the last part. Okay, yes, you gave us the end behavior, okay? So as x is approaching negative infinity, the bigger that x gets in the negative direction, our y's are continuing to increase. But as x approaches positive infinity, the graph is going down. So yes, that's the perfect description of the end behavior. Good stuff. She took the hard one, so there should be no issues now. Yes? Yes. Donnie, give me something.
Range is
Good stuff. Jay, give me something. I got intercepts, increasing and decreasing left over. Awesome. Alexis, give me something. I got intercepts and increasing left. 0, 0. And Kaylee, increasing. Not. There's none. It's not increasing anywhere, okay? And there you go. Analyze that graph very nicely. Questions? Okay? So don't forget, you can always fall back to making a table to graph something, especially if you don't remember what it looks like. Okay? But knowing about your coefficient and your degree, aka your exponent, you can know exactly what this graph should and should not look like. Okay? Now, when n is less than 0, okay? When n is less than 0, power functions like f of x to the x to the negative 1, x to the negative 2, so on and so forth are going to be undefined at 0. Okay? These functions will have some type of discontinuity. Because before, n was a positive number. Okay? It was 2, 4, 5, 6, so on and so forth. Okay? Those pictures from before only correspond if n is positive. But if it's negative, you're going to have some type of discontinuity. Now, the reason why these will have discontinuities is because, first off, whenever we have a problem that has a negative exponent, hopefully in your previous classes you've been told that you don't want to have negative exponents. Right? Have you ever dealt with negative exponents before? Has your teacher always told you to make them positive? Make them positive. Do you guys remember how to make an exponent positive if it's negative? Reciprocal. You basically turn it into a fraction, okay? So x to the negative 1 is basically saying 1 over x to the positive 1. Okay? X to the negative 2 is the same thing as saying 1 over x to the positive 2. Okay? You only want to deal with your positive exponents. So if you've ever given a power function where n is less than 0, make it positive. And then you'll realize that, hey, if I have x in the denominator, remember, you always set your denominator equal to 0 to find out, if there are any discontinuities. What type of discontinuity are we going to be dealing with these type of problems? When you have 0 on the bottom, what type?
Asymptotes.
Asymptotes, also called infinite discontinuity. Okay? Infinite discontinuity. And real quick before I turn the slide, if you're given something like this, how do you write this so that it's a positive exponent? Careful, y'all saying two different things. The negative exponent only applies to the x. So the 2 stays at the top, but the x goes to the bottom. It turns positive. Okay? So, whenever you're given a negative 1, write it as a positive. Let's look at an example. And we are going to graph. We're going to graph and analyze 2x to the negative 6. Now, before we start making a table, let's make our exponent positive. What's that going to actually be? Careful. 2 over x to the positive 6. Remember, that negative exponent only applies to the x, not to the number in front. Okay? So now when we make our table, everything we plug in for x, we simplify, we simply do 2 divided by that number. Okay? Do you guys think you got it? You want me to do it with you? Oh. You guys want to do it together? You want to do it on your own? Together? All right. So negative 2, negative 1, 0, 1, and 2. Do the same ones. Okay? Now when I plug in negative 2 and I raise it to the 6th power, that's already going to be an even positive number. Okay? Now you should already know that 2 to the 5th is 32 because we just did it, so raised to the 6th power is going to be 64. So this is going to be a 2, it's going to be 2 over 64. And can I simplify that? 1 over 32. Okay? What's negative 1 to the 6th power? 1. So 2 over 1 is 2. When I plug in 0, what happens? I'll get an asymptote. It's undefined. There is no y value here. There's an asymptote there. Not that type of asymptote, but a vertical. I just put a slash there knowing that. I'm going to have an asymptote. Not 0, 0, but all along that y value. I'm going to have a vertical asymptote right there. My graph is neither going to cross nor touch that line. It's going to get really gonna get? 2. And when I plug in 2, I'm gonna get 1 over 3. Yes.
So if there's that asymptote going down there, would that mean there's no intersection?
There's no y-intercept for sure. No. And not, in actuality, there's not gonna be any x-intercepts either. Because if I were to continue to plug in like numbers bigger than 2 or smaller than -2, it's gonna continuously give me a small number over a really big number. So it's gonna keep getting closer and closer and closer to 0, but never cross the touch. So at -2, I'm at 1/32, which is like really close to the x-axis, but not on it. -1, +2. 0, I have an asymptote. 1, 2, and 2, 1 over 32. Now I feel like, well, what is this supposed to look like? If you need to do more points, that's fine. But again, like I was just explaining to Brian, the bigger that x gets, it's going to be a small number over a really, really big number. Okay? So you're going to keep getting closer and closer and closer to 0. So this graph, kind of looks like your parent function, your reciprocal function. But it's both of them are going to be on the same side. Okay? Same thing here. Really big this way. There's that graph. You guys want to analyze together? Can you get the analyzation on y'all? Together on y'all.
Together.
All right. Domain. Well, clearly, actually, let's start with something else. It's not continuous, is it?
No.
It has what type of discontinuity? Infinite. At what value? At what x value?
0.
At 0. So if there is a discontinuity at 0, that affects your domain. So my domain is not negative infinity to positive infinity. It's negative infinity to 0 and then 0 to infinity. So I need to join that with a union. And it's not going to be defined as 0. That's so totally backwards. Alright. No bracket, because there's next to it. Range.
It's increasing.
Let's do what actually? Parenthesis around the 0 to infinity. Remember, the bigger that x gets, the closer and closer it's getting to 0, but it's not actually ever going to be 0.
Okay, so why would we start with 1 over 32? That's where our range.
Because these are just some points to give us an idea of what this graph looked like. So we could have plugged in -3, -4, -5, and -3 million.
So you just start at 0.
So with far range.
Right, yeah, far range.
Yeah. Do we have any intercepts?
No.
None, because it doesn't even cross the y-axis nor does it cross the x-axis. We come back to end behavior. Is it increasing?
Yes. At
Yes.
negative infinity, positive.
So negative infinity,
0.
but to 0. Remember, when we read from left to right, we're trying to figure out when this graph going up. And here, it's going up from negative infinity to 0. But after 0, it's going to be what?
Decrease.
Decreasing. 0 to infinity. Now our end behavior, we can go ahead and set it up. As x approaches positive infinity, the bigger that x gets, what's happening to y?
It's smaller.
Smaller
0.
to 0. And as x approaches negative infinity,
We're going to just
negative infinity, this way,
0.
to 0. So basically, remember, in behavior, what's happening at the ends? What's the y value happening? What's happening to the y values at the ends? They're getting closer and closer. You guys doing all right with this whole analyzing thing?
Yes.
After a while, you're going to start noticing a pattern amongst all of your power functions, okay? I'm walking you through this now, so in that way, after you do about 12 more, you're gonna be like, oh wow, I already know what this should look like because it's the same setup as all the other ones. Doesn't matter if there's a 2 in front or 3 in front, or if the degree is 2, 4, 6, 8, or if it's 1, 3, 5, 7. They all have a similar pattern. They all do the same thing. Promise. Yes. Yes.
If we do like a test thing on this, and we like get a bunch of questions in another book, you want us to graph still?
And most I'll probably have you graph like 4 of them. Okay? But hopefully after doing this so many times in our notes, in our homework and practice, you'll know that, hey, when you have a positive even number and an even exponent and a positive coefficient, it's going to look like this. Okay? And you know how to set that up. But this is kind of what you do if you forget what any of these look like. Okay?
Sort of like safety.
Exactly. Okay? I want you guys to do this one on your own. But before I let you do this on your own, let's make sure that we are applying the right function. How can I rewrite this?
2 over x root.
Very good. All right. This one looked kind of familiar, didn't it? It looked like what? The parent function. Which one? 1 over x. 1 over x looks very similar to this one, 2 over x to the third. You guys, the reason why I'm showing you this is because you're going to start to realize that there's a pattern, okay, based off of the exponent, whether it's even or odd, and then based off of the coefficient, whether it's positive or negative. You're going to start to realize this. Then you won't even have to really worry about graphing because you're going to be like, hey, I recognize this. This is just like our parent function, so it's going to already kind of look like that, okay? What values did you have, though? 1 over 4?
Negative 1 over 4.
Negative 1 over 4, sorry. Negative 2? Undefined 2, and then 1 over 4. So you had negative 1 4. Because when you plug in negative 1, when you cube a negative 1, it's still a negative. And then 2 over negative 1 is negative 2. You got positive 2?
No, I got a 1. I forgot the 2.
Yeah. So it's going to look like this. Maybe a little smoother. Okay? And then 1 you're at 2, and then 2 you're at 1, 4. And it's going to look just like our parent function. Because our parent function, 1 over x, has what type of exponent? Positive or negative? Not positive, negative. Even or odd? It's odd. So all your odd exponents that are in the denominator are going to look just like your parent function. But your even ones, when they're in the denominator, are going to look like this. Okay? Domain. Savannah, what you got? Look, what's the range? Not quite. To 0.
Oh, yeah.
Because it's not going to cross over that. And then intercepts, there is none. Because you do have a vertical asymptote. Yep.
So if there's a vertical asymptote, it's never going to hit like intersect ever at any point.
Not wherever that asymptote is. It's never going to cross or touch.
So it wouldn't cross the x-axis even if it were a vertical asymptote.
Well, horizontal is a little bit different. We'll talk about that when we actually get a little bit more into those types of functions after this one. But the vertical one is definitely not, never ever. Horizontal, sometimes. This clearly is not continuous. What type of discontinuity?
Infinite.
Infinite. At 0. Is it increasing?
No.
No. Is it decreasing?
Yes.
Where?
Negative.
Very good. I'm glad you guys broke it up. I thought you were going to give me negative infinity to infinity. No. At 0, it's doing nothing. But on the other side, it is decreasing. lastly, our end behavior. So as x approaches positive infinity, what is it? And as x approaches negative infinity, it is 0. Questions on power functions. I'm telling you, after you do enough, you're going to start to recognize the pattern. Then you won't even have to worry about really, having to make a table. Like I said, that's just like a safety net, okay? So if you forget what it looks like, you can make a table, plot your points, bam, you got your graph. To save you some time, you can remember what these look like.